It's very clear that all of computing is going to be about AI. In the next 3, 4, 5 years, 80+% is going to be this one workload. That's unprecedented.
We're approaching a world where a single workload, a deep neural net, could be running on 99% of computers. What are you planning to do different with unconventional?
We can get to biological scale. It's clearly possible. Our brains live in the physical world. The existence proof is there.
What might have naturally happened over the next 10, 20 years, we're just speedrunning. We're just compressing time. We're talking about 500 million raised.
Yeah.
Why?
We're running against fundamental limits of power generation. We need to be ready with a solution. We need to look at what we can build within a 5-year time horizon, because that's when the energy constraint is going to hit us.
And where's the brain on that?
I think your estimates for the market are way too small. reading your memo here.
You're seeing my return. Are you telling me that's conservative? Hi, everyone. I'm Guru Chahal, a partner at Lightspeed Venture Partners. And this is the Investment Memo, the show where founders reveal the stories behind their businesses and how they will shape the future of their industries. Today, I'm joined by Naveen Rao, co-founder and CEO of Unconventional AI. Naveen is best known for building and selling 2 deep tech companies, Nirvana to Intel and Mosaic ML to Databricks. And now he's taking on his most ambitious challenge yet. Unconventional AI is rethinking the very foundation of computing. As AI systems push against the limits of today's chip architectures and energy grids, Naveen is exploring new approaches to create a 1000x improvement in computational efficiency. Today, we'll discuss AI's energy crisis, why now is the moment to challenge Moore's law, and what it takes to build a company that could redefine the future of compute. Naveen, welcome to the show.
Thanks for having me.
I'm really looking forward to this discussion. You and I have known each other for a number of years, but we're going to give you a little bit of an insight into what does the rest of Lightspeed think about you as we decided to embark on this incredible adventure with you. So I'm going to give you the draft of the investment memo that we wrote.
Very cool.
But we were sharing how excited we were about your new project, and we'd love to go through this and perhaps through this share with our audience why we're excited, why you're excited, why this is the right problem for you to work on, and so on. And so as we do that, I'd encourage you to take a look at it, of course. But before that, why don't we start with a little bit of your background? And you have such an intriguing background that goes across industries, across stages. I'd love for you to highlight some sort of big milestones on that journey.
Yeah, first, this is great. It's rare that we get to see the sausage making a little bit. So I think it's fun for me to learn how you guys think about it. So my background has been, like you said, quite varied, but there has been a sort of a theme through all of it. For whatever reason, I got enamored with this idea that, nature came up with the concept of a computer in a sense, and somehow made something through a set of stochastic interactions through evolution that's highly efficient and navigate us through the world. That concept just always blew my mind. And, the fact that our brains run on 20 watts and, is everything we are just still seems amazing and magical to me. So I think that's been a motivating factor. And I learned that as an undergrad, and actually started to learn that, there's certain biophysics that go on inside the brain. And Carver Mead actually started to explore those biophysics and say, hey, can we build circuits that sort of act like this out of silicon? And at that time, that wasn't really clear because transistors were used for a very specific purpose. Like transistors were amplifiers, they're really linear. The brain is nonlinear mathematically in a lot of ways. So could you actually make these devices act that way? And turned out you could. And so that, again, kind of blew my mind. I did some, senior thesis work on this as an undergrad even. But, after graduating, you come out to Silicon Valley, you get a job, and I wanted to learn how computers work and how you actually build them from scratch. Of course, I was a computer engineer as an undergrad and computer scientist, but getting into actually building them, architecting real products, I think was very important to understand what the real bounds are. Like, what can we actually build? How long does it take? How many people does it take? How complex is it? These are questions you can only really get your head around when you've worked in the field. You have to really understand the state of the art. You have to do it.
Yeah.
So I worked at Sun Microsystems, worked on the UltraSpark 3 chips.
That's incredible, and most people don't realize this. Back at that time, Sun, Spark stations, DEC Alpha, SGI. I mean, this was incredible sort of compute level innovation.
Totally.
And so that's where you learn, how you take those incredibly innovative ideas and bring those all the way out to production.
Yeah, you're pushing the forefront. What's possible? I mean, back then, you called it symmetric multiprocessing.
That's right.
SMP, which is basically multiple chips. And this was before they really had multiple cores in a chip. And so making those interconnections work, making it cache coherence, this was the state of the art. We were literally inventing new things at that time. And so DEC Alpha was another one. They had the fastest processor in the world at that time.
Yeah.
Some of the best engineering I'd ever seen, right?
Yeah.
So it was a wonderful opportunity as a new college grad to be, kind of in the thick of that. And Sun ran things in much smaller teams than Intel did. And so I got exposed to a lot of things. I got to work with distinguished engineers and all of that. So it was really a great learning experience. But I started to see that, okay, I'm kind of getting my head around this, and I got a bit of the startup bug. I think a lot of folks who are younger in Silicon Valley still feel that. And I felt it back then, I was in my early 20s and left to go to a chip startup. We were doing reconfigurable processors. So I went through a series of different startups working on optimizing a certain workload for speed and efficiency and cost. That was basically the way you can think about moving a workload from a CPU and software to something in hardware. An obvious example was two-way video conferencing. Back in the early 2000s, you couldn't really do video compression on a CPU. It just didn't have enough cycles or enough horsepower. So we actually had to build this stuff in hardware. And that enabled you to do things like telepresence. So it was really enabling to be able to make something drastically cheaper. And so I kind of saw that early in my career.
This is interesting. This is the first time at that point in your career where you're moving from designing general purpose, high performance hardware to designing hardware that is customized for a specific workload.
That's right. Exactly.
That's a very interesting shift.
And people talk about ASICs today.
Right.
I mean, back then, it really was an ASIC. I mean, it was this idea that, CPUs can only do certain things because of performance. And so if I need higher performance, I build it.
Yeah.
So networking, video compression, wireless DSP, video content delivery, all these things. It was cool because as a hardware designer, I get to learn all of these other things, right? I learned cryptography as part of building backends like Mac layer chips for wireless networking, for instance.
Yeah.
So, it was kind of fun. You get to learn all this new stuff. You just dive in and have to implement it in hardware.
Yeah. But somewhere in the back of your brain is the obsession with brain.
It is. And through it all, it was okay, I know how a computer works.
Yeah.
I know I've sent them to the fab. I've gotten them back. I understand how all of these things work. Actually, even as an undergrad, I did device physics. So I kind of knew a bit about how transistors worked. And so that never quite went away. And so, after I turned 30, I was I really want to get back to this. And, family constraints make things harder. I had a kid and another kid coming and all that. But I actually quit my job, went back to grad school. And, most of my family thought I was crazy because I had a very good career in Silicon Valley. But really, it was just this long-term obsession of, I want to learn more about brains. Why do brains do things differently? How do we make machines intelligent? How do we make them efficient? That 20 watts just never left my head. So I actually went straight in to a PhD program doing computational neuroscience. And, I had to learn how to do neural implants, do neurosurgery. So took a whole class on how to do neurosurgery. I had to train animals like monkeys to do tasks, and we listened to neurons and then figure out how to decode what's going on in their brain. And what's interesting through it is that actually you learn about the biophysics of neurons. You learn about the neuroanatomy, how things are interconnected, the sort of microarchitecture of the cortex. And as an engineer, I could kind of view this and say, there's some interesting concepts here that we've never quite exploited in a synthetic system, in a computing system. So kind of got the gears turning a little bit. But I played scientist for a few years. But at the end of the day, I really am an engineer at my heart. I love to build things. And I don't think you really understand something until you can build it.
Yeah.
Just because you can write an equation down, to me, that's not sufficient. If I can build a system, it's okay, now I understand it.
My mom used to say, you do math through your hand, not through your eyes.
That's right.
You don't look at it, you actually do it.
The world is physical, right? You need to build these things and then it's real. I mean, everything else is imaginary in a sense, right? Until we built it.
Now you've gone through this journey of you're studying the brain, then you go into semiconductors. Not just general purpose, you go from general purpose semiconductors to custom semiconductors for a workload. Then you go back and study the brain.
Yeah.
How does that lead to Nirvana? What was the key insight? And what year was that, by the way? Because this is pre-ChatGPT. This is all of this cool stuff, right?
It's pre-deep learning, actually.
It's pre-deep learning.
So I went back to school in 2007, finished my PhD in 2011. So well before all of this. Now, we actually, in neuroscience and computer science, like there was a lot of overlap on this neural network side of things. I actually went to school to try to use neural network techniques to decode brain signals. In my essay, this is what I wrote in 2007. And when I got to school, everyone's like, neural network approaches don't work. Just use support vector machines. That's the future. I actually remember Jan LeCun giving a talk back then. It was kind of like, this is sort of a joke. It wasn't taken seriously, right?
Yeah.
And it wasn't until the ImageNet moment, which happened in 2012. And at that time, I was still connected very much to the academic world and actually was doing research at Qualcomm. So Qualcomm, unbeknownst to many, was one of the leading AI research labs. Google had spun up. There were a number of neuroscientists there. And Qualcomm was trying to build neuromorphic architectures for low power. I went there as a research position after my PhD. Actually, I was a quant for a year, but we don't like to talk about that. Really trying to build low power neuromorphic architectures. And that's when we started seeing all the ImageNet stuff happening. And I was like, look, I think we figured out now how to make a learning system work. Now it's about scale. And to me, scale goes back to my early career. Like, I know how to make things scale. I know how to make them faster. And so can we think about neural networks as a computing motif that we can actually build a new computing platform around?
Yeah.
And that's where Nirvana was born, was I want to build a chip architecture that's designed for neural networks from the ground up. And so we came up with this idea of a two-dimensional architecture. Like a normal architecture of a computing chip is, a 1D register file. And I load and store from memory, and I compute like scalar quantities like
add, subtract,
multiply, divide. But we thought about it like, well, neural networks can be written as linear algebra, so matrix math, and we can make a whole architecture that's devoted to two-dimensional math. It seems silly now because everyone's like, yeah, duh, it's obvious, right? But at that time, it was not so obvious, right? Yeah. And at that time also, GPUs did not have tensor cores. That came after we did this in reaction to it.
Yeah.
So we were one of the first ones to do it. Actually, turns out Google was thinking along these lines as well. We started Nirvana at the beginning of 2014, almost identical timing to when the TPU project started. The TPU was not public yet. We started to learn that Google was actually going down this path as we were talking with them. We were like, hey, we want to do some research collaborations, and they're being cagey about the hardware side of things. So we started to figure out that they were working on the TPU at the same time. So we kind of came with the same concept at the same time.
Yeah.
But we were the first AI chip startup to do this.
And that was an incredible ride. You sold that company to Intel. And so we go from this experience now, in addition to the previous, you've now added this experience of designing hardware built to run neural nets. You sell that company, you start another company called Mosaic.
Yep.
What's that all about? And what was the experience you gained out of that experience?
Well, I mean, yeah, so sold Nirvana. I ran, I started and ran a new AI division inside of Intel, learned a lot about, scaling up organizations and things like that. And actually saw that the problem was going to be that neural networks we've figured out scale. We saw the Transformer paper, right? I was like, we've now figured out scale. We're going to do something really cool with that scale. It wasn't clear yet that we're going to build ChatGPT. That was not done yet. So 2018-ish, in the industry, I knew it. And so the Nirvana chips were actually designed from scale from day one. They were actually a scale out architecture. But we knew that was going to be a problem. And then making that fast, cheap, and accessible was going to be an issue. Like, we had the thesis then that everyone is going to need some level of customization for their neural networks. Some people might need a lot. And in fact, we kind of use an analogy to Silicon Foundry, where you have a CPU as a dominant paradigm, but then you have this long tail of ASICs, which people need to get performance or reduce costs or whatever. Similar thing will happen with foundation models. So we knew that even in 2020. This was the problem that we wanted to go after. So I actually reached out to Jonathan Frankel, who had published a paper called The Lottery Ticket Hypothesis. And myself and Hanlon Tang, who was also a co-founder of Mosaic, we thought this paper was really cool because it really laid out some kind of fundamental science around how neural networks learn. And we felt that we could exploit that to get pretty massive efficiencies on existing hardware. And if we could package that, make a platform out of it, we could own that layer, basically. That was the thesis of the company.
And that's what you ended up doing. So now you get this first foray into the software layer as well, deep understanding of where the cutting edge, the frontier of neural nets in today's age is. You sell that company to Databricks. You've kind of come full circle. Silicon experience, deep understanding of the brain, building silicon for neural nets.
Yeah.
and then rebuilding neural nets for today's silicon.
That's right.
Right? So you come full circle. Tell us about unconventional. Why is now the right time before we get to unconventional? What is happening in the industry that is different from the last 10, 20, 30, 50, 60 years of computing that makes you go, you know what, I need to do something new? What's the why now here?
I think we're in this unprecedented time from two perspectives. One is that it's very clear that all of computing is going to be about AI. We've hit the inflection points of this is useful. It took a long time to get there. Like when I say a long time, 10 plus years. But I think ChatGPT, the reason it was such a big moment was that it showed the world, the lay person was like, oh my God, this is something that's actually useful. And now we're figuring out how to make that useful for various industries, verticalize AI, et cetera. But it's clear that this is going to be very useful. And very useful means it's going to have a ton of demand. The demand is exponential. So all computing flops are now moving toward AI. In the next 3, 4, 5 years, 80+% is going to be this one workload. That's unprecedented.
Right.
Also, it's unprecedented that kind of demand is driving so much computing being installed that we're running against fundamental limits of power generation. So we've never been in this regime before. If you go back to the 40s when the first digital computers were made, nobody cared about how much power it took. I mean, I think it was a megawatt back then. And back then it was a lot for a megawatt. And you didn't care about this. It was more about what's possible. I will throw all the energy I can at, because you didn't have a limit per se. It was a very tiny proportion of the total amount of power generation even back then. So it wasn't until the last couple of years that we start thinking about, wait a second, I can't build a data center because I can't get power.
I mean, the way I think about this, these two are really good points, right? The one thing is we've never had a regime in which a single workload has dominated compute in this way. Like as long as you and I have been in compute, we were talking about this earlier, it's always been a massive diversity of workloads that are running on these devices, typically CPUs. And now for the first time, we're approaching a world where pretty much every new compute cycle is dominated by a single, highly distributed, homogeneous workload, a neural net. That's it. Everything is just a neural net. And we've never seen that before. So that's one. But where does the power issue come from? Is it because we're trying to fit a square peg in a round hole? We're trying to fit neural nets onto a regime which was built for a different kind of workload? Where does the power constraint come from?
So actually, it's exactly what you're talking about. We had this diversity of different workloads. And general computers, digital computers, are numeric. They basically do arithmetic on numbers. And so that paradigm became something that we could apply to many different domains. I could simulate physical systems. So I could do some sort of numerical physical simulation. I could do accounting software. The first workload that was used for ENIAC in 1945 was artillery trajectory calculation. The value proposition was literally the fact that they could do it faster than somebody else. If I can do that faster, I get better aim and I take my target out, right? So that was the value prop. And this is very different than where we are today. So at that time, I had all these different workloads. I need to build something very general. And actually, this tension existed when I was at Intel. Is like, CPU is a general thing. It can do all these workloads. I would say that's true, but the reality is all the workloads are going to move to AI. And so everyone's like, no, that's not going to happen. It's like, well, it's happening, right? So now we're at this weird place where we took the existing paradigm that's numeric and deterministic, and we're using that for the basis of AI, which is not numeric or deterministic.
Yeah.
And this is providing a massive inefficiency because we have all these abstractions that were built for other purposes. All of this diversity of workloads is kind of irrelevant, as you said. Like now we have this one dominant workload that actually doesn't look like the other ones.
Yeah.
So it's time to rethink what that fundamental platform looks like and rethink it with respect to power, to efficiency.
So over the next 5 to 10 years, we have a situation where 90, 95, maybe 99% of all workloads are just neural nets.
Yeah.
And they're running on a silicon substrate that is way more general purpose than it needs to be.
That's right.
And that then becomes the source of that inefficiency. It's sort of like, jack of all trades, master of none.
That's right.
So it can run a lot of different type of neural nets and a whole bunch of arithmetic and a whole bunch of databases. It can do all of that.
Yep.
But it's not really amazing at any one. How wide is this gap? Are we talking about there's an opportunity to do this 2x better, 3x better? Where do you think is at least the theoretical limit for how much more efficiency we can get if we design the substrate the right way?
So it's interesting because this kind of goes back to the very physics of computing generally. And there was actually a lot of theory put forth in the 1960s around computing. That's when computer science was kind of born and proliferating. And right around the time that Claude Shannon did information theory, there was also a related theory called the Landauer principle or Landauer limit. And really the idea was like, can we establish a theoretical lower bound for computing? So that's hard because you have to define what computing is. And so they define computing as a erasure of a single bit of information. So if I do that and then I say, well, how many erasures do I have in a given computing system? Can I then compute a lower bound? So that lower bound maybe never feel physically realizable really, but you may be able to get close, kind of like the Shannon limit. So if I took an existing NVIDIA B200, we're about 9 to 10 orders of magnitude away.
Oh, wow.
So that's 1 billion to 10 billion X away.
9 to 10. And where's the brain on that?
So again, this is not completely settled science, but the brain is likely within 1 order of magnitude of the Landauer limit.
Oh, evolution 1?
Yeah.
0.
That's right. There's 2 things it says. One, it says like from where we are today, we have a long way to go.
Yeah.
And we can actually get to biological scale. It is possible. It's clearly possible. Our brains live in the physical world and they're there. So the existence proof is there. We have to engineer it. We have to build it. What's also true, and what I think is interesting, is I think we can exceed biology. If we learn the principles and actually start to engineer this, like we can iterate our way to something
Because you can
better.
accelerate evolution in some sense. Like,
Exactly.
So theoretically, that should be possible. 11, 12 years ago, you took on that same challenge and you said, I'm going to build silicon substrate that is built for neural nets.
Yeah.
Why is this different? What are you doing differently this time than, say, 2014?
So 2014, just to contextualize for people, a VC had not seen a hardware startup in 10 years. So at that time, this was right in the middle of the SaaS era. It's when SaaS was the best thing in the world, right? So I come out and pitch a hardware startup for machine learning that no one's ever even heard of. In 2014, almost no VC knew what machine learning was. So when I pitch this, people are like, this makes no sense. I don't know what machine learning is. I don't know if it's going to be important, much less building hardware for this thing, which is going to be super capital intensive. We got burned on all these networking investments 10 years prior. So at that time, we had to be extremely capital efficient and build the next increment of things, which was using digital, using ASIC approaches. Like there are ways to build a chip that are much more straightforward, but have less performance. And at that time, like I said, a GPU didn't even do tensor math yet. So we had a lot of headroom from the current paradigm. So we just had to beat the current paradigm. So at that time, I think we raised something like $24 million before we got acquired. And the first raise, our Series A was 3.3 million. And we were trying to build hardware. So that is not straightforward. And we needed to be as efficient as possible. I mean, I would stay in shitty hotels and all the things you have to do to keep.
I think that's the salary of one AI researcher right now.
I think it is. It is. It's totally right. And it's just weird because then this was backwater and AI researchers didn't get paid a lot of money at that time. Google started that process at that time. It became a little bit hard. But anyway, so from that point to this point, I think the market has become very clear. Everyone knows what AI is now and every investor knows what it is. And also because of Nirvana and the exit we had, that actually spurred investment into a whole bunch of other hardware players. So I think now VCs are pretty well versed in understanding that hardware is a critical component. And of course, now the biggest company in the world is a hardware company.
That's exactly serving the AI market.
That's right.
Yeah. So I think the opportunity set is very clear. Technically, what is different? What do you want to do with unconventional? With Nirvana or with, frankly, any AI accelerator company today, it is still a little bit of, we know how to do compute cycles. How do we build a chip that is slightly more efficient at doing matrix multiplication, et cetera? What are you planning to do different with unconventional? Because clearly the current paradigm is not taking us closer to the brain.
That's right.
In fact, we were talking earlier about there's about 8+ billion people on the planet today, 20 watts per brain. So that's what, 165 gigawatt of total compute in humanity today.
Right.
If we build 165 gigawatt of data centers with today's technology, do we get closer to the aggregate compute capacity of every human on the planet?
I think it's not even close.
Not even close.
I mean,
probably by several orders of magnitude.
9 orders of magnitude.
9 orders of magnitude. So what do we do differently? What does unconventional do differently?
Yeah, this is exactly the question we asked is, can we kind of rethink those foundations? And what I mean by that is actually go back to the very beginnings of computing and say, can I actually start to use the physics of the underlying medium? In this case, silicon. We can talk about why silicon, but physics of the underlying medium to actually subserve that compute. So what we do today in a digital numeric system is we simulate those kind of dynamics. So we have a ReLU function or a GeLU function, and we have some algorithm that runs, but it's simulating something that looks sort of like a brain. If you look at a brain, it doesn't have these abstractions. It doesn't have a neural network layer that's written in software and then running on a substrate. It's literally using the physics to do the neural network implementation. And by doing so, you actually get a lot richer dynamics as part of the physics of the neuron that we still don't really understand how it connects to computing. But what we do understand is there are certain circuits that exhibit properties that are somewhat similar from a dynamical systems perspective. We can talk about that if you like, but they have some of the same properties as large-scale neuronal networks. Can we now connect that to the back-end compute of an artificial neural network? And by doing so, can we actually build something that's vastly more power efficient simply because we're using the physics directly? We're not simulating it through numerics, we're actually using the physics. So to answer your question, is it matrix multiplied? Not really. You could analyze these systems as with linear algebra, and you can basically say, oh, it's effectively doing linear algebra, but it's not being implemented as such.
That's right. The brain is not doing matrix multiplication. The brain is not doing linear algebra. The brain is just doing brain things. And so the question is, can you build a substrate that's like that?
Exactly.
And this is one of my favorite parts of the conversation. If you look at our memo, there's a section in there on constraints. Because obviously, if you show up at Lightspeed and say, I want to build a brain, there are questions around, is that doable? Is that scalable? Like, what are the bounds of this? What's the science risk? I'm sure you, before we were having that discussion, you were thinking about this with the core founding team. What are the constraints that you wanted to put on yourself so that what you're working on now can actually see the light of day? Like, how do you constrain this so it doesn't become an open-ended exploration for, can I just grow a brain the way a human grows a brain?
That'd be great. But yeah, actually, I had this discussion with you before even my co-founders, right? A while back. And I think the main considerations are, and this has been true for every company I've started, has been like, you've got to do it with time as an element of your vision. People like to think about vision and timing as different. I think they're one and the same, because there's a relevant thing today that may not be relevant in 50 years, but you have to do that today to get to that 50-year mark. So today, we need to sort of look at what we can build within a 5-year time horizon, because that's when the energy constraint is going to hit us. Mm-hmm. So we need to be ready with a solution. Now, what does ready mean? Ready means I didn't just solve a science problem. If I solve a science problem, great. If I can't scale the manufacturing of that problem, I cannot have a global impact. So I need to be both ready and scalable in manufacturing in order to have the impact. So I want to have impact in the next 5 to 7 years or 5 to 10 years. I need to be able to scale that up, start creating an ecosystem, selling into market, having people buy it, building a product that people care about, and being able to scale up to demand.
Right.
So with those constraints, that kind of leads us to a place where, okay, there are certain places we don't go. Like, we don't actually have to go and build whole new devices that we need to write down new physics for.
There's no massive material science research needs to be done. $10 billion fabs that need to be built. You're focused on technologies that once there is conviction that this is the right path, you can drop it into the existing sort of manufacturing supply chain and it just scales right away.
Exactly. And there's lots of green field in this area of circuits and dynamics that no one's really explored.
Yeah.
People who know circuits and silicon don't know anything about AI. People who know about AI don't know anything about circuits and silicon. So largely what we're doing is, coordinating this effort across those different domains and getting people to talk.
Yeah.
And I literally have to deal with, people talking past each other because they can't understand each other. It's a different language.
That's a great point, right? It's such a different kind of team because you are one of those unique individuals that has that background across biology, how brains work, how traditional silicon, AI silicon, and models work. But that's very few people. So now you're taking absolute experts across different domains. Yeah. that's probably one of the biggest differences from even Nirvana to some extent, where you've got a very heterogeneous sort of team of experts, a mixture of experts.
Mixture of experts.
That you have to then coordinate.
That's right.
Another thing I was thinking about is, so one constraint was, let's focus on technologies that hit that level of performance, that level of efficiency, but can be scaled with today's methodologies.
That's right.
A second constraint we were talking about, I remember in some of our brainstorming discussions, was this difference between frontier technologies that have unbounded science risk and near frontier technologies that have a lot of the science risk removed, and now it's more of an engineering risk. Is this the appropriate technology for this task? And then can it be scaled or not? Help us understand that a little bit, and what constraint did you put on yourself and on the team?
Well, I think those open-ended ones end up being 10-year kind of journeys.
Right.
And if we kind of go back to the time constraint, like it's a very clarifying assumption. When you say 5 years, it basically says what you can do and what you can't do. And we have to be near frontier. We have to take pieces that exist today and we know how to build, but put them together in new ways. So it's like we want to focus on that aspect of it as opposed to building something fundamentally new from the physics level. Now, that doesn't mean we're not breaking new ground. Like people haven't really built neural networks with dynamical systems. That is somewhat new. There is literature out there about how to do this. And we're going to exploit that and build upon it. But it's absolutely possible to do. That's already been shown. So we're not taking things that no one has ever thought about before and making it work. We're taking the components and actually engineering them together to make something that's going to fulfill a purpose.
Yeah.
That's why we say 1,000x, because if I really wanted to go crazy and say I'm going to whole cloth build a new, device, a new substrate, not even silicon, then I can go for a 1,000,000,000x. Why not, right? But that's not realistic in today's environment. But I think we can lay the foundation and groundwork to say, okay, we're going to break the abstraction stack we have today and build up a new one, build this on existing manufacturing capabilities, and open the door to new materials over time.
Yeah, I think this is what I've always enjoyed about our conversation. I mean, it's, there's sort of these three layers we talk about at Lightspeed. There's the technology, the product, and the business. And you're one of the few founders we work with at that hardware abstraction layer that's able to seamlessly cross back and forth. So placing these constraints is so important because you're right. From a pure technology perspective and an intellectual simulation perspective, maybe you and I work on something that has that $1 billion opportunity. But if it's not a business, then it's a lot less interesting because the impact you're going to have is somewhat limited. And that's what I really like about what you're doing with Unconventional, which is, we're going to take a big swing because it is the mother of all markets. Yeah. It is the biggest market there. It is one of those few markets that can create these multi-trillion-dollar opportunities, but we're going to go about it in a bounded way.
Yes.
We're going to constrain ourselves on time and the kind of things we do. And I think that's a really neat way to think about it.
In academia, it's interesting because there's this idea of like, I will have influence over the world and impact by publishing a paper, or publishing work. I played a scientist for a while, but I actually find that building products and getting people to use them is a much greater influence. It's very hard for a paper to have influence. It can, but it's very hard for that to happen. Whereas if you build products and you get people using it and you learn from those products and make them better, that's how you change the world.
Yeah. So you've got a great team that you've already put together. You're looking to hire more.
Yeah.
This is a call for more resumes, I suppose. Please reach out to Naveen. What's most important over the next 12 to 18 months?
Yeah, that's a great question. And, because this is a sort of 5-year journey, we need to learn. We need to optimize for learning first. And learning means iteration to me. So building an iteration machine internally where we can say, okay, we're going to propose some ideas. They're going to be founded in, maybe papers and other things. We're going to do a bunch of simulation and get comfortable with it. And then we're going to go build it and test it.
Yeah.
Then we're going to feed back that learning and do it again and keep doing it again and again and again. And that's how we'll get to something where it's like, now we have very high confidence. Now we know I can build this circuit and it's going to do this and it's going to behave that way when I manufacture it. Like we need to get that level of certainty before we build a product. I think a lot of hardware companies out there have somewhat skipped these steps. I think like it's been about, oh my God, I got to go try the hardest thing I can do, but then not really thinking about how to build it at scale. We want to actually do this properly because we do want to hit that scale in 5 years. So right now it's about hiring the people who are deep experts at multiple parts of the stack, not one person being expert across all of them, but experts in different parts, like silicon engineering, analog design, system architecture, like how I put these circuits together, compute modeling, how I deal with noise, how I expose a hardware software boundary, and then AI systems, how I map neural networks onto different kind of computing substrates. There's almost no one who knows all of those things, but we're looking for experts in those various areas who have interest in learning the rest, right?
Yeah. It's like creating a new Pareto frontier.
Totally.
By finding spiky people on each point on that line and then just bringing them together under the same roof. So you have something that's bigger than a sum of the parts.
That's right. And having some kind of binding way for them to communicate. And really, we're trying to do that through code and simulations. Like, you think about it like this, like, okay, well, let's write it in code and simulate it.
Yeah.
It's like, oh, now I understand, right? It's sort of like writing things in math, and it's like universal language in a sense. But because everybody has their own way of thinking about these problems. And it's actually fascinating to see how hard it is to get people to communicate.
Herding cats?
Oh, yeah. It's like herding cats and squirrels and frogs, trying to herd them all together.
Yeah. But what an incredible opportunity. One way we've talked about this before, one way I've thought about this is, we're taking what might have naturally happened over the next 10, 20 years, and we're just speed running time.
Absolutely.
We're just compressing time. Let's do in 1 year what might have happened over the next 10 years of research in small academic labs here and there, with no communication with each other, limited funding, and so on. Actually, that reminds me, your first, so what did you say was the Nirvana first round? How big was the Series A?
Series A was 3.3. The seed was $600,000.
$600,000 seed, 3.3, total of about $4 million of capital across those 3 rounds.
Yeah.
We're talking about $500 million raised.
Yeah.
Why?
Because we need to iterate. We need to build prototypes and we need to fail. Like, we need to try things out and see how they work, why they work, where they don't work. It's not dissimilar to frontier labs in a sense where their space of iteration is trying things on GPU clusters.
Yeah.
I think OpenAI is something like $4 or $5 billion of GPU spend per year. Training one model doesn't cost anywhere close to that. But all the iteration and all the things that didn't make it off the cutting room floor, that's what that $5 billion is for. And in the same way, we need to try a bunch of things. We're going to throw some stuff in the trash, but we're going to learn on every iteration.
Yeah.
And that's how we're going to solve this problem. And speed running is exactly the right way to look at it. Like, these things have been going on in academia for a while, but it's shoestring budgets. You have a grad student who's never designed a chip before trying to learn how to, make a circuit work and, using free tools from the internet. No. Let's do this with professional people who are deep experts and just give them what they need to try things.
The example in the back of my mind has been, and you'll see this in the memo. In fact, in one of the sections in the memo where we talk about returns, et cetera, you'll find the other reason. So one is, you need this capital because you're running all these experiments, because as we share right there on that page is, I think of this as where OpenAI was circa 2016, 17 timeframe.
Yep.
We have no technology religion. We will try anything that has odds of working. Let's run these experiments. And as you know, we're pretty close with Anthropic. That's literally to your point about OpenAI. Anthropic is the same way. The core goal is no technology religion. Let's run experiments that make sense and then pick the ones that are working and scale them and see how far that takes us.
Exactly.
And I think that has to be the same ethos. That's why we need the resources, because we're compressing time. And then the other reason, frankly, is because it makes sense. Look, at the end of the day, we're running a business, you're running a business. It makes sense because if you can speed run 10, 20 years of research into a year or two, the opportunity to go from this investment to an incredible outcome is there.
Yeah,
because
absolutely.
The market needs it now. We're going to hit that power wall in a few years. And so we need to speed run this, because when we are ready, the market will be ready. We know that. It's actually quite rare in venture, right?
It is.
You invest in something where you're like, the market's there. The market's pulling this thing from me.
Yeah.
It wants me to succeed, which is so rare. So that's probably the single biggest reason why I'm so excited. I mean, this is just such an incredible time.
It's all internal risk. It's technical risk, not market risk.
Yeah. What kind of people are you looking for? Who should we send your way? Who should reach out to you?
I mean, crazy people for sure. Obviously, I mean, you have to be someone who thrives on that unknown and wanting to, grope around in the darkness to some degree. At the beginning, that's really important. So, people who really get a high from learning and figuring out new things and are creative, right? Over time, as we go to production and all of that, then you want people who are really good at the details and focusing on that, that last 1%, all of those things. But right now, it's interesting. A lot of the people we have been in careers where you're focused on that 1%. It's like, guys, don't focus on the 1%.
Yeah.
Let's try 10 different things versus trying to optimize one.
If you're an incredible individual in a small academic lab in the middle of nowhere with a shoestring budget, boy, don't you want to play with the big boys? Like, we can do something really interesting here.
We can. All the things you wanted to try, you can try them.
This is it. It's like working in Tony Stark's Iron Man lab.
Exactly.
Because you get to try everything, which is incredible. Now, you and I, we've known each other for a while. I used to think you're about as boring as I am, completely all geek and all nerd. Turns out you're not. Turns out you've got some pretty interesting hobbies. Tell me a bit more.
Well, I think you got to have almost like throw a noise term in to like make your brain work in interesting ways. I love to race cars. I loved cars sort of since I was a kid. And so, some of it I think just comes back to being an engineer. Like, it's like, how do you make something go fast? How do you make it have more power? It's almost a similar thing, but there's an element of the physical part of driving and the honing something to perfection. That's just very appealing. And so I do race cars at a pretty high level. I've done Le Mans a couple of times. And
I hear there's a Silicon Valley tech ecosystem racing mafia around. Is that true?
There is, yeah. And some of us meet up at the races. We race against each other and, race hard on track, but then we'll go to dinner together, afterward.
I got to get into this.
It's
maybe
pretty
I'll
fun,
stick
actually.
To my knitting. This has been incredible. All of our discussions are just incredible. But hopefully, so many of the topics we discussed, you got an insight into how we were thinking about the problem. We've literally gone down. If you look at the investment thesis, those first 4 points, we've literally gone down in your experience, how it brings together this ability to stitch silicon, software, neural nets, brain into one person, so you can sort of think about and make those connections on how we should connect these things together in new and innovative ways. Right. I think that's a key part of the thesis. Your ability to attract incredible talent, as you did with Nirvana and Mosaic, is a key part of it. We spoke about the why now. Why now? Like, in 60 years, we haven't seen a situation where a single workload has dominated even a few percentage points of the global compute footprint. Like, I can't think of a single one, not even a few percentage points. And we're approaching a world where a single workload, a deep neural net, could be running on 90, 95, 99% of computers 10 years from now. So that's why now. And then we discussed, the size of prize here and what the headroom. The headroom is so much. We're just trying to fit the way a brain computes onto processed sand.
Yeah, absolutely.
There's a big difference between, the art of what's possible here and where we are today. So it's really exciting, Naveen. I could not be more thankful that you chose to partner with us. I could not be more excited to see what comes next, and I think it's going to be an incredible ride. So thank you.
I think so, and I'll leave with one parting thought. I think your estimates for the market are way too small. reading your memo here,
you're seeing my return. Are you telling me that's conservative?
I think it's conservative.
I'll drink to that.
Well, if we solve this problem, I think there's going to be new markets opening. Like, I think robotics are something that will hit its stride in the next decade.
I think you're absolutely right.
You need local compute. And frankly, I'm a motor control neuroscientist. A dynamical systems chip that powers motor control would just be amazing. Like, if I could be a part of that happening, it'd be amazing. I think that's going to be a market, and we need these new kind of processors for this sort of thing. I think
there's one thing that has always, we're students of technology, we're students of the technology industry, and one thing we've noticed over and over and over again is every time you make a critical component in the technology industry cheaper, faster, better, the TAM explodes.
Yeah.
Explodes by not just 2x, 3x, 4x. We're talking about 1 to 2 orders of magnitude.
Yeah.
So I think you might absolutely be right. Again, we're geeky, nerdy people. We'd like to be conservative in our projections, which are already, as you can see, incredible.
Yeah.
But those projections, you're right, are based on our assessment of where current sort of market is headed over the next 5 to 10 years. But I think that current market evolution is constrained by the abilities of today's technology.
That's right.
And what we're building at Unconventional unconstrained, unshackles that market. I think you're absolutely right that the eventual end market could be 1 to 2 orders of magnitude larger than what we're even projecting today.
Absolutely. Yeah.
This has been fun.
Absolutely.
You're going to take me out racing one of these days?
Sure. Anytime.
No.
Take you on the racetrack.
Not getting in that car with you. But I will watch you from the sidelines.
Perfect.
This has been fun, Naveen. Thank you so much for joining us.
Thanks for having me.